Military operations typically involve working with partners to resolve rapidly evolving situations where adversaries are adapting their tactics, techniques and procedures, and the behaviour of the civilian population is changing. Thus, military information processing systems need to be able to recognise significant patterns of activity which are distributed in time and space in near real time without generating too many false alarms. In the language of information processing, this requires the ability to recognise the relationship between a set of individual events. Deep learning-based AI systems are constantly improving their ability to recognise such individual events. We've developed techniques which enable two key capabilities. Firstly, humans can inject new knowledge or hypotheses about patterns of activity through the addition of new rules, which means patterns can be recognised in situations where there's insufficient time or data to train a deep learning model. Secondly, there's a significantly reduced need for training data, especially important when examples of the patterns of interest are relatively rare. Other benefits include faster AI model training and improved detection accuracy over pure deep learning approaches. We emphasise loose coupling of hybrid kinds of AI systems in an open architecture, and the resulting applications can run on edge of network devices, so are suitable for tactical sensor systems. The research is intended to enable defence to process in near real time streaming data from a future Internet of Battlefield Things, and to adopt AI systems which learn and adapt at the pace of the fight, necessary to ensure our tempo of understanding and action is not overmatched by our adversaries. In this presentation, we demonstrate the research in the context of monitoring a rapidly evolving situation in the NATO Anglova urban setting via diverse AI assets processing multimodal sense data with management of situational uncertainty.
This is a quick demonstration of the early work towards the Adapting AI Systems to Recognise New Patterns of Distributed Activity demo. This demo shows a situational understanding example based on the collaboration between human and machine agents in a human-agent knowledge fusion environment. The purpose of this environment is a place where human and machine agents can rapidly build and exchange knowledge through tellability, informing new information, or explainability, going deeper into explanations of why information exists or has been added. The separate demo named Enabling Rapidly Formed Human-Agent Coalition Teams Through Extensible Information Exchange covers this environment in more detail, should you be interested in the underlying research principles that have informed its construction. What we're seeing here is a number of services that we have defined earlier. We have the Anglova Boulevard CCTV service, a situational understanding service, which is generic and trying to make sense of the situation in the city, a central square listener service, and a media monitoring service. These first two, Anglova Boulevard and Central Square, are specifically located based on the sensors they are connected to. The media monitoring service is focused on social media, specifically looking for angry comments or posts, and is tailored to the particular region within which Anglova is located. The canvas on the left-hand side provides a set of capabilities and services that can be used, customized or extended, and shared as needed for each use case. For example, here we have the standard core entity types, as well as specific additional extensions to support coalitional situational understanding. We'll be seeing each of these 4 CSU types created and interconnected as the story progresses. A service is the machine AI services that have been deployed into this environment, usually in a distributed setting onto the sensors themselves, but they could also be run remotely in cloud infrastructure. An explanation is the additional information from the service which provides some form of explanation for any events that are detected. Uncertainty. In real systems, all observations and inferences come with uncertainty information, which is essential in terms of any downstream inferences or human assessment. And finally, events. The events that can be detected by services in this environment. These are specialized into a number of concrete types based on the capabilities of the services, so explosions, violence, shooting, and situations. There are also various other sections with supporting concepts, and all of these can be extended by new services, new configurations, or human activities. There are also files and functions which can be used to extend the core story, but these are not covered in this demo. Finally, there are numerous ways to interact with the information in this environment. For example, if we navigate to the map, we can see we have a couple of sensors located, an audio sensor on Central Square and a CCTV camera here on Anglova Boulevard. And this is within the Anglova city setting, within the NATO vignette, and we'll come back to the map later. There are a number of core views, and it's easy to extend with custom views, palettes, and AI agents as needed. Okay, so let's see what's happening in Anglova based on the services we have deployed. All the services are running, and we can use this environment to get more information about them and see what's happening as they create events. We can see here that the Anglova Boulevard CCTV service has observed an active shooter situation. The explanation for the event contains links to the relevant raw input from the sensor, which in this case is the CCTV video and audio feed. This can be played in situ should the analysts need to see and hear this for themselves. The analyst may be unfamiliar with this particular service, and especially in cases where the input feed does not match their expectation, may wish to see an explanation from the machine agent regarding why the active shooter event was inferred by the deep neural network service running on this sensor. This can be seen on the canvas as the SAVER, Selective Audio-Visual Relevance explanation, which takes the form of an attention-highlighted video showing the audio and visual relevance of the scene. Full details of the SAVER research can be seen in the corresponding demo named Real-Time Explainable Artificial Intelligence, Time Series and Multimodal Data. The ability to see this machine-generated explanation in both the visual and audio domains may be very useful for the human analyst in terms of building their trust in the service, especially if they are able to feed back their reaction, positive or negative, in any case, thereby increasing the training data for this service. Let's briefly look at this uncertainty for this event, which is summarized as likely some confidence. You can see the certainty is made up of belief, disbelief, and uncertainty values which sum to 1. You'll also notice a rationale which indicates the certainty was downgraded because the partner is trusted at 80%. This is because the sensor and service is run by the local Anglovan authorities, whereas the coalition user maintaining situational understanding is from the UK. The certainty is initially expressed by the service itself as source uncertainty, but upon ingestion into the platform is converted into actual uncertainty, with any modifications made as needed and summarized in the rationale. This information is all available in the graph, but is hidden by default to ensure that the users are not overwhelmed but can navigate to any relevant information as needed. The analyst has seen this shooting event and would like to upgrade the situational understanding service to be particularly focused on any discussion on social media that may indicate increasing unrest, specifically by looking for anger in posts. This is a technical update and would likely be made by an operator user who has responsibility for maintaining the services, but this environment can also support the input of higher level information from which such code as this can be generated. After reviewing the current configuration, the user decides to extend the rules with a further clause for anger detection, and link this into the configuration. This could either be done by extending the existing configuration rule or by creating a new additional node as shown here. The rule is now live and has updated the running service accordingly. As time passes, the anger detected on social media increases and a threshold is passed, causing an event relating to threats of violence to be generated. This service is run by the US coalition member and is fully trusted by the UK, hence the source uncertainty of likely some confidence is unchanged when ingested into the system, with the rationale reflecting this. The explanation shows a particular example of an angry social media post that led to the inference of the threats of violence event. Due to the earlier rule change, the Situation Understanding Service is also triggered, creating a situation based on both the active shooter event and the threats of violence from social media. Initially, the uncertainty is likely with no confidence, with the rationale being noted that this is computed from component events which are indicated via the is explained by links from the active shooter and threats of violence events. The rules continue to run and the situation will be updated as any new related events are detected, with the certainty being revised accordingly. Finally, an explosion event is detected based on the audio sensor located in Central Square. As with all detected events, a link to the explanation is shown along with the original audio should the analyst wish to assess the event for themselves. This AI service is very confident, generating a very likely, certain classification for this event, and since this listener service is run by the UK, there is no modification to this certainty. The event is also linked to the unfolding situation due to the spatio-temporal proximity, and the certainty for the situation is updated accordingly. Mark will now explain some of the scientific details of the listener service and how it was able to detect this event. Mark will spend up to 3 minutes talking about some of the science of his area of work. Returning to the bluff slide, Alan will spend up to 1 minute summarising what we've seen in the form of an outro. Thank you.